In computer graphics, performance is very important for things like video games. Video games usually measure the performance in the number of frames rendered per second. In this assignment, I used the steady state frames per second to measure performance of my program. Because VSync was disabled, the number of frames per second could easily reach values higher than 60 Hz, which is the value of my monitor. There were a few things that I was particularly interested in investigating. The first was a higher resolution lighting. In the previous course, we learned about OpenGL's built-in lighting, which is a per vertex lighting that is not really all that customizable. In order to make the lighting look more decent, using this method, you had to increase the polygon count of the things you wanted to render, thus increasing the number of vertices, allowing more points for the light to hit, and that also caused the polygon count of the model to increase, and thus the resolution of the model to increase. In GLSL, however, it is possible to do per fragment lighting, which can give a much higher resolution light without needing to increase the polygon count. Because the lighting calculation is much easier for the per vertex lighting, the time required to render each polygon is much quicker. But in order to get a fair visual comparison, the target model must also have a lot more polygons, which more polygons requires more time to render. I decided to investigate which of these effects is more dominant. I used 3 different types of renderers. The first is a simple OpenGL program without any shaders, using the built-in lighting. This one is used as a control for the other 2. The second one is a per fragment shader, and then the last one is a per vertex shader. My scene includes objects which all have a resolution value which roughly correlates to the distance between the vertices on the model. So for example, it's like a grid. I took measurements of the FPS for each rendering mode at various resolutions of the model. Visually, I determined that the per fragment shader at resolution 32 looked the same as the per vertex shader at resolution 128, which in turn looked comparable to the OpenGL shader at resolution 256. This makes sense because the OpenGL shader is the least customizable and requires the highest resolution of model to actually look decent. So in order to have a fair comparison, I needed to compare the frame rates of the scene at these various levels of resolution instead of the frame rates at the same resolution, because some of them don't require the high resolution models in order to look good. So I'm more going off of visuals than actual resolution values. The results are shown in these figures. Each figure is the FPS versus the number of lights for the corresponding mode. Each line represents the values at a constant resolution. It's not surprising to see that the higher resolution models have fewer frames per second. As you can see, the blue line at the top is the mode run with resolution 1, and the green line at the bottom is run with resolution 256. So you'd expect the high resolution ones to have fewer frames per second. So also notice that the maximum frames per second for the OpenGL standard is the highest, followed closely by the per vertex shader, but the per fragment shader is actually really far down. It's really slow. Also notice that the OpenGL standard seems to be the only one that is affected by the number of lights. There's just something unsettling about these results, something that's not quite right about them. These results made me question how I had the test set up, so I went back into the code to try to figure out what was causing this strange behavior. In particular, the GLSL programs, they're not affected by the number of lights, which just doesn't seem right. And why would the fragment shader be the slowest, even with low resolutions and high resolutions, for example? Why would we ever use it if it's so much slower? So I thought there might be something wrong with my code, and I look back, and that brings us to the next thing, which is conditional and loops. Looking at my fragment shader, I found my mistake. When allowing users to toggle the number of lights, I put a bit mask and a loop in the fragment shader, which I was thinking, well, that's not that bad, but actually it is, as we'll see. On the GPU, loops are bad for several reasons. Unlike the CPU, there's no branch prediction, which means each iteration of the loop must wait for the test conditions to complete before moving on. In addition, there is no pipeline, so each instruction is executed sequentially. Lastly, several different threads execute in the same warp will have the same program counter. Thus, if multiple threads on the same warp traverse different paths, each thread must wait for the code to execute those paths instead of just skipping over it. This would indicate that you want to unroll your loops. Doing so, however, increases the amount of code required to be retrieved by the host system. Recall that memory transfers are very expensive. I need to know what is more important, keeping your code space a few pages shorter by using loops, or reducing the memory transfer times, but having loops and unneeded instructions that cannot be pipelined. To test this, I set up two new shaders. The first one contained only one light and no loops, and the second one contained all 8 lights, but still no loops. And then I compared those results with the corresponding shaders, the corresponding fragment shaders that each had 1 light and 8 lights using the while loops and the if conditions. What I found was actually pretty shocking for how OpenGL works. The results from this test, from the first test, was that only having 1 light in the scene resulted in 13 frames per second when it was hard coded in. But with the conditional, the result was only 3 frames per second. So the only thing I could think of is that OpenGL doesn't actually optimize any time. It actually does the worst case scenario regardless of what the values are, because if you look at the code here, these values shouldn't be changing for any of the threads in the warp, so the program counter I would have thought would have skipped it, but it doesn't. And so you have to be really careful about your fragment shader, because it will always seem to execute under the worst case scenario, even if none of the threads take that path. If I were to guess why this happens, it's because the GPU probably doesn't have an aggregate function across all the threads in a warp. So it may not know if any of these conditions are actually taken or not. So as a result, it probably has to just do them all anyway because of that lack of having an aggregate function. This would make sense with their design decision to keep each core relatively simple and use that chip real estate instead for having more cores instead of having more complex cores. After running these tests, I want to look more at the differences that can occur in the fragment shader because of how you programmed the fragment shader. The reason I focused on the fragment shader is because the fragment shader has the largest amount of time on the GPU, and so the changes in it will have the largest effect in the performance. And this will help me know exactly how the GPU is used and how to most optimally write code for it. The way I did this was by measuring differences in the frame rate depending on the complexity of the lighting. Notice how the light used in the scene doesn't use a standard cone. I started with a light that only uses the standard point light, but this didn't really work for my scene because I didn't really like the look of that. It just doesn't look very realistic, and I wanted to go for a little bit more realism. I really like the look of spotlights, for example flashlights, so I decided to try to make a light that looks more realistic by modeling a flashlight. I started by writing a fragment shader that would limit the light to the cone directly in front of the spotlight. This effect can also be done in OpenGL's built-in library as well to obtain some similar results. So I did that just for comparison. The thing about this lighting is the sides of the light, they're very sharp and boring and don't really look all that realistic. So I decided to add a fall off on the side of the the lights, which is a step in the right direction, but this light still looks a little bit too perfect to be real. If you look at a flashlight, there's a lot of imperfections in the beam, so I wanted to model those. So I added another sine function to get those internal rings so that it didn't look too perfect to be realistic. And then I compared the various frames per second of these lights to see how they affect the performance. The frames per second are shown under each of these images here with the corresponding image of what those lights actually look like. The farthest left has all the effects, so it has the specular as well. This center one is without the specular, and the far right one is just the removing that cool little inner ring. As you can see, removing all the algorithms is actually the fastest at 11 frames per second. Then adding specularity only reduced frame rate a little bit to 9 frames per second, but then having that specular added another cross product into the calculation, which had pretty big impact and brought it down to 6 frames per second. So it's debatable as to whether or not I'd even want that specular to be in the scene. I think it looks just fine and without it, as the center one is actually my favorite looking one, and seeing as the performance isn't that much slower than the one to the right, I'd probably go with that one, but I guess that's user preference. I automated all of these tests so that they can more easily be run on slightly different hardware and slightly different algorithms. To conclude, here are the results of the final algorithm. As you can see, the number of lights, the resolution, and the type of shader all have an effect on performance. Most importantly, however, is how the shader is programmed. As you saw, optimizing just 1 or 2 lines of code could really make the difference between having a slow program and having a really fast one. Thank you for your time.